So let's do some fluid dynamics just a little bit, and we'll introduce another concept. This is called flow rate. It's not the same thing as velocity, and you'll just have to get that right by sort of thinking about it a little bit. We usually use the letter Q for the flow rate, and so Q is dV dt, where V is the volume. So it's the rate at which volume is maybe moving through your system, right? And so you might have a pipe for water that sends out 10 gallons a minute, or something like that, or 20 gallons a minute. That's the flow rate. It says nothing about the velocity. However, it's related to the velocity, and so this is we're going to talk about how, right? And so here V is the volume. So this is a pipe, right? And my pipe has area A, and I'm just looking at a little at some point P, right? And so I'm watching the flow go past point P, and in time delta t, this much of the flow, delta x of the flow, goes past P, right? And so my flow rate, Q, is the change in volume over the change in time. And again, that's volume, not velocity, right? And so the change in volume is just delta x times the area, because delta x times the area is the amount of volume in here, right, divided by delta t, or it's the area times delta x over delta t, which is the area times the velocity, where again, this is the velocity. If I made this infinitesimal, then I would say dx dt, right? And that's the idea, right? And so the flow rate is the area times the velocity. So imagine now that I have a pipe that has a narrowing in it, right? And so I can say, look, this is area 1, and this is area 2, and this is flow rate 1, and this is flow rate 2, right? But if you think about this for a second, if this is sort of a steady state system where water is just flowing in and flowing out, then in any sort of steady state system, if this thing's been running for a while, how much mass volume per second is coming in here has to equal the volume per second that's going out there, as long as the fluid is incompressible, right? And so Q1 and Q2 have to be the same, right? And that means area 1 times velocity 1 is equal to area 2 times velocity 2. And then I can say, well, V2 is equal to V1 times area 2 over area 1, which means that if this guy, sorry, got that backwards, area 1 over area 2, thanks for the correction. If this guy is 4 times the area of this guy, then the velocity of this guy has to be 4 times greater, right? And so that's why when you get a narrowing in a tube, you get a faster velocity, right? For round pipes, most pipes are round, V2 is equal to V1 times pi R1 squared over pi R2 squared, which is V1 times R1 over R2 squared. So if this pipe has twice the diameter of this pipe, the velocity here is 4 times greater, right? Twice the diameter means 4 times greater. 3 times the diameter means 9 times greater. Doesn't matter if I'm talking diameter or radius, the ratios are the same. And so you can see that wider velocity, wider pipe gives you a smaller velocity, and a narrower pipe gives you a much larger velocity. So we're going to talk about Bernoulli's principle. It's a very important principle in fluid mechanics, and really what it is the work energy theorem for fluids. If you remember, we said that net work done on a system is equal to the change in kinetic energy plus the change in potential energy of the system. We're going to make a little more calculus-y argument here, but it's basically the same thing. And so we're going to look at work done, and so work done, potential energy, and kinetic energy. And this little system here is set up for this. And so I've got a large pipe that narrows and goes up. And so the fluid in here undergoes a change in potential energy because it's rising, right? This is like the up direction, right? And it undergoes a change in kinetic energy because the pipe is wider here and narrower here, so it has to speed up where it's narrower for conservation of flow rate. And so I get a change in kinetic energy because of that. I get a change in potential energy. And there's a work done. Even though the fluid is moving continuously, it's the fluid behind your section that's pushing you forward, and you're getting pushed back by the fluid in front of you. And so as fluid moves through, it's getting pushed from behind and pushed from the front the whole time. And so we're gonna use all of these quantities to figure out this for the fluid. And so what we're going to do is we're going to take this section of fluid that between my two index fingers. So it starts here, it goes all the way up to here, and it ends here. It's just an imaginary section of fluid in the continuous stream. A short time later, this section of fluid has moved on, and now the back end of it is here, and the front end of it is way up here, because even though it's the same section of fluid, the top end has to move faster because it's in a narrower pipe. And so it's stretched out in the front. And so at the bottom it's moving with a velocity v1, and the top it's moving with a velocity v2. Notice that this little section where it's moved in the bottom is dv, that dv is also the same volume at the top. And we could say, dv is equal to area 1 dx1, and that's equal to area 2 dx2. That is to say, these two volumes are the same. When this thing gets pushed up to here, the front end gets pushed out to here. Right? And so the first thing we're going to do is we're going to calculate these pieces one at a time. And so the first thing we're going to do is calculate dw net. And it's the net work done. And so the net work done is the work done by this force acting on from behind minus the work done by the force acting in the front. And so it's just the work is force times distance times cosine theta, but the theta is 0 in this, or 180 degrees in this, and so this will just have a minus sign on it. And so we'll say, look, this is F1 dx1, that's the work done by this guy, minus F2 dx2. That's the net work done by the two forces that are acting on my little section of fluid as it moves, right? And so this is pressure 1, area 1, dx1, minus pressure 2, area 2, dx2. That's equal to pressure times dV, pressure at 1, minus pressure at 2 times dV, right? Where once again, V is the volume. So the net work done is the pressure times the volume for the two acting in opposite directions. So it's the difference. Right? And so now let's calculate the change in kinetic energy, right? And it's just equal to Ke2 minus Ke1. It's how much kinetic energy this piece gained minus how much was lost when we left that one, when we moved from here to here, right? And so this is just 1/2 times the little, we can call this dm. These two guys have the same mass, right? It's just the density times the volume, right? Times V2 squared. It's this guy's kinetic energy minus 1/2 same mass times V1 squared, and that's equal to 1/2. The dm is just rho dV, so it's rho d volume V2 squared minus 1/2 rho d volume V1 squared. You see all that, maybe? Okay. And so the change in kinetic energy is just the kinetic energy gained when the object moves, when the fluid moves up to this piece. So it's gained here minus lost here, and so it's Ke2 minus Ke1. And those kinetic energies can be just written as 1/2 mv squared, where they each have the same dm, right? And it's 1/2 mv2 squared minus 1/2 mv1 squared, where the m's are dm's. And notice that dm is equal to rho times d volume, right? And so I can write this, the change in kinetic energy, as 1/2 rho dv times v2 squared minus 1/2 rho d volume v1 squared. Right. I can do the same thing with the potential energy. dPe is equal to, so PE2 minus PE1. It's the potential energy gained from this piece minus that lost from here, and so it's equal to dm times g times y2 minus dm times g times y1, right? Potential energy is mgh, and so the masses are dm, g is g, and the height is just a y. And so, again, this is rho dv, that's what the masses are, right? Times g times y2 minus rho g dv, sorry, dv g times y1. And so if you take a big picture of this, dw net, this is what we're going to do on the next screen. Here's my work done. It's P1 dV minus P2 dV. That's the work done in this equation. And then it's equal to the change in kinetic energy, which is this piece, plus the change in potential energy, which is this piece. And so that's what I'm going to start with. I'm going to erase the screen. I guess I'll just do it while you're watching, right? And so what I want to say here is this is rho. So the work done, which is P1 dV minus P2 dV, is equal to the change in kinetic energy, which is this term, 1/2 rho dV V2 squared minus 1/2 rho dV V1 squared. I can erase that guy. Plus this guy, that's my change in potential energy, plus rho dV G Y2 minus rho dV G Y1. And so now I've taken my work kinetic energy theorem and I've applied it to my fluids. And the first thing I want you to notice is that every term has a dV in it. And so I can cancel all of these dVs. Everybody has a dV. All the dVs go away, right? And what I get is P1 minus P2 is 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho G Y2 minus rho G Y1, right? This is now my work kinetic energy theorem for a fluid. And so now I'll erase all of this up here, I guess. And what I'm going to do is I'm going to put the things with 2 subscripts on the right-hand side and the 1 subscript on the left-hand side. I'll put my Y2 on this side over here. And it says P1 plus 1/2 rho V1 squared plus rho G Y1 is equal to P2 plus 1/2 rho V2 squared plus rho G Y2. And so this is all the information about these guys, and this is all the information about these guys. And what this is saying is that is Bernoulli's principle. This is Bernoulli's principle. Since it doesn't matter which points I pick, I can pick any points in the fluid. I pick these 2, but I can pick any others, and I get the same result here. What it means is that if I evaluate P plus 1/2 rho V squared plus rho G Y at any 2 points in the fluid, they're the same. And so that means they have to be constant. And so P plus 1/2 rho V squared plus rho G Y is constant in an enclosed fluid. And that's Bernoulli's principle. So we can do Bernoulli's principle for a static fluid. Remember, Bernoulli's principle is P plus 1/2 rho v squared plus rho g y is equal to constant. Right? If the fluid is static, that is to say not moving, then this piece is 0, and we just get P plus rho gy is constant. And so if we look at the manometer we were looking at a little while ago, we can have a fluid in here, and this side's attached to some pressure P2, and this side is maybe open to the atmosphere. That might be what P1 is. And so we can, if we have a height difference, we can use Bernoulli's principle here, and we can say, look, since it's constant, that means if I pick point 1 plus rho g y1 is equal to P2 plus rho g y2, right? And I'm just going to show you this gets us the result we had before. This gives us P2 is equal to P1 plus rho g times y1 minus y2. That is to say, I subtract this over to the other side and factor out the rho g, and I get this. And so y1 minus y2 is this height here, the thing we called h when we were looking at manometers. And so P2 is equal to P1 plus rho gh. And that's what we got when we solved the manometer problem. So for a static fluid, Bernoulli's principle gives us exactly what we already had. So we can also look at Bernoulli's principle for a horizontal pipe with a narrowing. And so here's the kind of thing we were talking about before, and we have, right, we can have area A2, and over here we have area A1, right? And so I have V1 in this region and V2 in this region, right? And we can say, well, look, if I use Bernoulli's principle, I can say, look, P1 plus 1/2 rho V1 squared plus rho g y1 is equal to P2 plus 1/2 rho V2 squared plus rho g y2. And if these things are concentric, right, then y2 and y1 are the same if I'm just looking at a simple case for the horizontal pipe, and I get P1 equals P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared, right? Now we know that V2 is much, much larger than V1, or is at least larger, right? It's larger to the extent that it's narrower, and so P2 is equal to P1 plus 1/2 rho times V1 squared minus V2 squared. And that means that in the region where the pipe is narrower, I necessarily get a lower pressure because V2 is greater than V1, and so V2 squared is going to be greater than V1 squared. And so this quantity is going to be negative, and P2 is going to be at a lower pressure. This is the heart, you might say, no pun intended, of the problem with coronary arteries. In a coronary artery, you get a narrowing if somebody has atherosclerosis, and so if you might have a vein that looks like this, right? And it's just got some area here, A, and it's moving along at some speed, V. Well, gradually, you get some buildup in this coronary artery, like this, and now, you call this 1, and now I have an area here, this A2, with V2, right? And again, V2 is greater than V1 in this region, and so the pressure in this region is less than the pressure in this region. Well, arteries are sort of having to hold themselves open because there's other materials in your body that are weighing down on it and want to compress it, and so it needs a certain pressure here to stay open. And as this thing narrows, the pressure gets lower and lower because the velocity gets faster and faster, and eventually the pressure won't be strong enough to keep the artery open, and it'll shut the artery off, and then your heart doesn't get any more blood, and you have a heart attack. And so there are lots of examples where I'll do some calculations where you can look at the pressure difference due to fluid flow. So here's a Bernoulli problem with a horizontal hose. So a hose has water with speed 2 meters per second. That's inside the hose. Then 25 meters per second at the nozzle. So as it's leaving, it goes out at 25 meters per second. This is the standard problem we were talking about earlier, where if you narrow it, the velocity has to be greater. Right? It works when you put your thumb over a hose, for example. Since the pressure at the nozzle, where the stream enters the air, is at atmospheric pressure, in other words, it's going into the air here, and so the pressure around it is atmospheric pressure, and so that's the pressure. Determine the pressure inside the hose. And so we want to know the pressure back here, and so we have these two regions, region 1 and region 2, and we could just use the Bernoulli principle across them, recognizing that since the hose is horizontal, we can cancel rho g y1 and rho g y2 because the two heights are the same wherever we measure from. Right? And so since we're looking for P1, this is P1 is equal to P2 plus 1/2 rho V2 squared minus 1/2 rho V1 squared, and that's equal to 10 to the 5th pascals, plus I'm going to do two steps here. First, I'm going to factor out the 1/2 rho out of each of these terms, and so that's 1/2 times 1,000 kilograms per cubic meter times 25 meters per second squared minus 2 meters per second. That one hardly matters. Squared, close parentheses. So that's the whole thing squared. And so this is roughly 625 times 1,000, which is 625,000 divided by 2. It's about 310,000. And so what I get for this is P1 is equal to about 4.1 times 10 to the 5th pascals, or about 5 atmospheres. Oh, sorry, about 4 atmospheres. Something like that. So this is an airplane wing, and it also uses Bernoulli's principle. Here's the idea. I have an airplane wing that has air passing over the top of it at 40 meters per second, and air passing under it at 38 meters per second. If the old-fashioned wings, the kinds you see on like a Cessna, as opposed to a single-engine plane that you see flying around, as opposed to like jets and fighter jets and stuff like that, those old-fashioned wings are flat on the bottom and curved on the top. And what that does is it forces the air going over the top to take a longer path, and that makes it have to travel faster. And so you get a higher velocity of air over the top of the wing than under the bottom of the wing. And Bernoulli's principle results in getting a lower pressure on the top than on the bottom. And that creates lift. That pushes the wing up. And so if the wing has an area of 40 square meters, suppose it's, 2 meters wide and a meter wide, what would it be, 2 meters by 20 meters, say, or something like that, roughly speaking. What is the net upward force on the wings, right? And so we're going to use Bernoulli's principle here. Here's Bernoulli's principle. Oh, the density of air is 1.29 kilograms per cubic meter. And so this is my equation for Bernoulli's principle, where I'm looking at P1 plus 1/2 rho V1 squared plus rho g Y1 equals P2 plus 1/2 rho V2 squared plus rho g Y2. And for this problem, I'm just going to dismiss these two terms. They're smaller, so the density is small. The density is about 1, g is about 10, and the thickness of a wing is less than a meter. So this is going to be a pretty small number. These other numbers are going to be around 100 or something like that, I think, when we're done. And so I'm just going to let those go and not worry about them. And so if I want to calculate the net upward force, I want to look at the difference between the upward force on the bottom and the downward force on the top. And that's how I calculate both of those. And so the net upward force is just F1 minus F2. It's the upward force from the bottom minus the downward force on the top, which is just that minus that, which is that. And so I know the area, that's 40 square meters, and so I need to calculate P1 minus P2, and I can use the Bernoulli principle to do that. Subtract the P1 over this side, move the 1/2 rho V1 squared to that side, calculate that guy out. It becomes 1/2 rho, which is 1.29 kilograms per cubic meter, times 40 meters per second squared minus 38 meters per second squared. Maybe I can write that better. Maybe not. I guess not. And what I get for that is about 100 pascals. And so I can put 100 in here, multiply it by the 40 meters squared. That gives me 4,000 newtons. It's 4.45 newtons per pound. So this might be 900 pounds of force or something. So it's a reasonable amount of lift. You know, it's not going to be enough to keep the plane afloat, but it'll keep it from sinking too fast. And so that's how you get a glide on a plane, using Bernoulli's principle. So here's another Bernoulli problem. An above ground pool has a small hole in the side. So here's the hole in the side, 1.5 meters below the surface of the water. What is the speed of the water leaving the hole? And so it's a small hole, so the water isn't sinking really fast or anything. So it's a tiny hole. And so once again, we can use Bernoulli's principle. We can pick 2 points. Sometimes you have to be judicious about what points you pick, but I can pick the surface of the water and this point here, and I can say, look, P1 plus 1/2 rho v squared plus rho g y1, that is at the surface, is equal to P2 plus 1/2 rho v2 squared plus rho g y2 right here at the exit. And the first thing you can notice is both P1 and P2 are atmospheric pressure. Pressure at the top of the water is atmospheric, and just as you leave the hole, just like the nozzle of the hose was, and back out in the air, it's atmospheric pressure again. And so those two just cancel each other, right? I have that on both sides, I can just cancel them. And so now I'm looking for V2, and so I can write 1/2 rho V2 squared is equal to 1/2 rho V1 squared plus rho g y1 minus rho g y2. And since V1 is at the top of the water, that velocity is just 0. And so this gives me 1/2 rho V2 squared is equal to, and so this just becomes rho g times y1 minus y2. You can see it doesn't matter where we measure from, because it's just y1 minus y2. It's the height difference between these two. And hopefully you would expect that that would be what determines the, there we go. Maybe I wasn't on it quite. I may have taken up too much space. All right, anyway, that's my y1 and that's my y2, right? And so next thing I can do is I can cancel the rows, because they're on both sides. And this gives me V2 squared is equal to 2g times y1 minus y2, or V2 is equal to the square root of 2g times y1 minus y2. Now, I don't know if you remember, but this comes from the kinematics problem that we did way back in chapter 2, where we said v squared is equal to v naught squared minus 2gh. This is the height. The velocity of this is just as though you had dropped it from that height, and so it's the square root of 2gh. Maybe that sounds familiar to you. It's why I always encourage you to solve problems using equations, because they will come back and you will, as old friends, you will recognize them. And so this is the square root of 2 times 10 meters per second squared times 1.5 meters, right? And so 2 times 1.5 is 3, times 10 is 30 meters squared per second squared. So that's going to give me meters per second when I take the square root of it. 30 square rooted is about 5.5. So that's the speed of the water coming out of the hole. Those are a few Bernoulli problems.